React but Maintain Your Equilibrium Part 2 is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. In React but Maintain Your Equilibrium Part 1, we learned that the equilibrium constant for the reacting ideal gas mixture is equal to the system pressure raised to the overall stoichiometric coefficient for the reaction, times the product of the mole fractions of each species raised to their stoichiometric coefficients, and K is calculated as the exponential of the negative of the Gibbs energy of reaction over RT. Now that we have all of these cool equations, let's do an example. Carbon monoxide and oxygen are fed in equimolar ratios to an isothermal combustor. If the reaction to carbon dioxide proceeds to equilibrium, calculate the fractional conversion of CO and O2 as the reactor temperature varies from 300 Kelvin to 2500 Kelvin. Additional data are that the reaction CO plus 1/2 O2 goes to CO2 and vice versa, and that the Gibbs energy of the reaction for this reaction is given by delta G naught equals negative 281,885 plus 85.678 T in joules per mole. Substituting the temperature's expression in for delta G naught and dividing R in units of joules per mole Kelvin gives the natural log of K equals 33,903 over T minus 10.3047. which has the same form as the temperature's expression for constant delta H naught from part 1. From the chemical reaction expression, the stoichiometric coefficient of carbon dioxide is -1, of oxygen is -0.5, and of carbon dioxide is +1. The overall stoichiometric coefficient is -1 minus 0.5 plus 1, or -0.5. Substituting into our expression, we get that the equilibrium constant times 1 bar to the -0.5 times the pressure to the 0.5 is equal to the mole fraction of CO2 divided by the mole fraction of CO and the square root of the mole fraction of O2. We have to calculate the mole fractions in terms of the extent of reaction for this process, so we are going to do that for each species. For a steady-state reactor, in is the molar inflow and out is the molar outflow. Were it a batch reactor, they would be the initial and final moles. We've done it without the dots on their flow rates and extents, but you can add the dots if you like. We'll start with the mole fraction for CO. The mole fraction is the number of moles of CO at the end of the process divided by the total number of moles at the end of the process, which is equal to the moles of CO into the process plus the stoichiometric coefficient times the extent of reaction divided by the total number of moles in plus the overall stoichiometric coefficient times the extent of reaction. Likewise, for YCO2, we have NCO2 out over N out is equal to NCO2 in plus the stoichiometric coefficient times the extent of reaction divided by the total number of moles in plus the overall stoichiometric coefficient times the extent of reaction. Likewise, for YO2, we have NO2 out over N out, which is equal to NO2 in plus the stoichiometric coefficient times the extent of reaction divided by the total number of moles in plus the overall stoichiometric coefficient times the extent of reaction. So what is missing from our set of equations? You need the system pressure and either the number of moles of O2 in or the number of moles of CO in, since they are equal but unspecified. We will pick a basis of 1 mole for either of them. We will also assume that the pressure equals 1 bar, which is not an unreasonable pressure for a combustor. Substituting in the expressions for the mole fractions, we get this rather complicated expression with the YCO2 on the top and YO2 on the bottom, with YCO raised to the 0.5 power on the bottom. And that's equal to K times the pressure, 1 bar, raised to the 0.5 power. The choice of 1 bar does make this problem slightly easier. Doing the simplification of the mathematics, we get that 2 minus 0.5 times the extent to the 0.5 power over 1 minus 0.5 times the extent to the 0.5 power times the extent over 1 minus the extent is equal to K. Since we're going to have to use this expression in the limits as the extent approaches 0 and the extent approaches 1, we need some simplifications. First, for the extent approaching 0, we can see that the 2 minus 0.5 extent approaches 2. The 1 minus 0.5 extent approaches 1, so that ratio approaches the square root of 2. The 1 minus extent approaches 1, resulting in the extent being approximated as K over the square root of 2. For the extent approaching 1, we can see that the 2 minus 0.5 extent approaches 3/2. The 1 minus 0.5 extent approaches 1/2, so that ratio approaches the square root of 3. Divide both sides by the square root of 3, multiply through by 1 minus the extent, and doing a little bit of algebra. The extent is either K divided by the square root of 3 over 1 plus K over the square root of 3, or 1 minus the extent equals 1 over 1 plus K over the square root of 3. In between, you can either use nonlinear root finding or choose values for the extent of the reaction between 0 and 1. Calculate K and then calculate T. Often when graphing a nonlinear equation, solving the inverse equation makes the plotting easier. The spreadsheet is linked in the reference webpage for the video. See the video description. The details of plugging these numbers into a spreadsheet and doing the calculation is not terribly interesting, so we'll present you with the graphical version of the results. The first thing to note is that the equilibrium constant, which is the orange curve over our range of 300K to 2500K, ranges from about 10 to the 39th down to 10, so we're only covering 38 orders of magnitude. And 1 minus the extent, which is showing how close the extent comes to 1, ranges from 10 to the minus 45 at 300K up to approaching 1 at 2500K. Translating those numbers into mole fractions shows that the mole fraction of CO2, CO, and O2 remain fairly constant all the way up to almost 2000 Kelvin, at which point the CO2 starts to drop and the CO starts to climb. If we look at the fractional conversion, which was our original interest here, we see that the fractional conversion remains remarkably close to 1 for the CO, meaning that we have principally CO2, up to a temperature of just under 2000 Kelvin. At that point, the fractional conversion begins to drop slightly. The fractional conversion of oxygen remains pretty constant at 0.5 until almost 2000 Kelvin, at which point it begins to drop a little bit as well. Without some sort of catalyst, the kinetics are so slow that the CO and oxygen will not react appreciably below 850 Kelvin. So, the equilibrium reactor will vastly overpredict the extent of reaction at lower temperatures. To account for the kinetics requires the next set of videos, How Did You Think I Would React? And Wishing Upon a Sea Star. However, we wanted you to have some idea how fractional conversions and extent of reactions are affected by chemical thermodynamics, and that engineers can't simply specify them. You have to deal with whatever nature gives you. The takeaways from this video are: 1. For ideal gases, the equilibrium extent of reaction can be calculated from the equations for the equilibrium constant K in terms of mole fractions and temperatures. 2. Equilibrium constants change by orders of magnitude for relatively small changes in temperature. 3. Solutions of these types of equations often require finding numerical roots of nonlinear equations. 4. Chemical equilibrium predictions without kinetic information can be seriously wrong. Thanks for watching. This video was brought to you by the DOFPro team.